Okay, thanks, William, for the opportunity to come speak here at the All Hands to give a sort of update about what we've been doing in the E3SM Cryosphere simulation campaign. As we're wrapping up V1, so I'll talk a bit about that. And then I want to focus more on, since the V2 tag was just recently created, how our simulation campaign is looking for V2. So to sort of start with just a high-level overview of what the goal of the science campaign is. Our science driver is how do rapid changes in the cryosphere systems evolve with the Earth system and contribute to sea level rise and increased coastal vulnerability. Our specific V1 science question was, what are the impacts of ocean ice shelf interactions on the melting of the Antarctic ice sheet, the global climate, and sea level rise? So for our V1 simulation campaign, we focused on fully coupled, low resolution simulations with pre-industrial control conditions. And the key distinguishing feature of the cryosphere science campaign is that we utilize a capability that extends the ocean domain to Antarctic ice shelf cavities. And once we have ocean properties under the ice shelf, we can then use these to calculate prognostic ice shelf basal melting. And what we quickly found out is that the fidelity of these simulations, in terms of this new coupling of these ice shelf basal melting calculations, is pretty dependent on getting the Southern Ocean properties right or less wrong. So to sort of highlight what exactly these changes to the Antarctic ice sheet runoff are, in the standard E3SM configurations, there's no active land ice component. So what happens to essentially precipitation that falls on the Antarctic continent, either as snow or rainfall, is immediately routed to the nearest coastal grid cell. There's a small storage factor in the solid or in the snow precipitation, but it's not very much. So essentially anything that falls on the continent is immediately routed to the ocean. There's some horizontal smoothing applied, but as you can see in the top two panels here, it's largely just distributed around the coast. In the cryosphere configurations, we replace these with the representations of the actual processes by which fresh water from the Antarctic ice sheet is distributed to the ocean, to the rest of the climate system, and that's through two processes: ice shelf basal melting, which, as I mentioned, we calculate prognostically, and the other is through calving of icebergs. And for that, we've implemented a prescribed iceberg meltwater data forcing set. So you can see in the middle two panels here, the spatial, so these are climatological averages, and the spatial distribution is quite different. And then in the bottom panels, I'm showing monthly climatology time series, and I'll just focus on this bottom left panel now to show the differences in the seasonal timing of the runoff. So in the standard configuration, these black lines represent the magnitude of the liquid and solid runoff. So you see most of the runoff is happening during austral winter as storm snowing onto the continent, whereas in particular the iceberg meltwater forcing has a strong seasonal cycle where most of that melting actually occurs in the austral summer. So our cryosphere overview paper for these B cases, we submitted to James on January 6th of this year. It's currently in its second round of revisions, and this focuses on two fully coupled, originally 100-year simulations that we've recently extended to 200 years, and which I'll talk about in a minute. But so the key points for the paper are the first, sort of showcasing this new capability, because this capability of being able to calculate prognostically ice shelf basal melting in an Earth system model is a unique capability of E3SM within CMIC class models. The second is that the simulated basal melt rates we've seen a strong sensitivity to the ocean mesoscale eddy parameterization. So essentially, there's a strong sensitivity to the ocean state that we found this knob of changing the mesoscale eddy parameterization helps us avoid a tipping point behavior under one particularly large ice shelf, the Filchner-Ronne ice shelf, which can transition to a very high melt regime, which was presenting a problem in terms of having a stable configuration in pre-industrial control conditions that would allow us to move forward into historical and other scenario forcings. So during the review process this year, actually, as we were exploring some of these coupling terms during our V2 simulations or early V2 simulations, well, we found a bug in the sign of the latent heat flux that the ocean was receiving due to iceberg melting. So essentially the ocean was slightly warming rather than cooling due to iceberg melting. Once we discovered this, we immediately reran the simulations, and the key points of the paper still hold, although the main climatic event of interest in the paper, which is the Filchner-Ronne ice shelf tipping point behavior to a high melt regime, which we successfully mitigated. That happens about 90 years later, but otherwise, all of the other key points hold. So we're now in the process of, we've just sort of finished rerunning these simulations and are swapping them out in the paper, but everything should still hold. And I'll just briefly mention that there's also a second paper that's focusing more tightly on the Filchner-Ronne tipping point behavior in G cases. So that's active ocean ice only with prescribed data forcing. And so that's also in preparation. So I'll just present a few results from the paper that is in review. And so these figures are still from the original simulations because we haven't had a chance to put together these full analysis for the rerun simulations yet, but again, the behaviors is essentially the same. So the two fully coupled simulations that we ran were first what I'm going to refer to as CGM, and this is the default configuration, where we use a constant GM parameters, which is the mesoscale eddy parameterization. And when we did that, we found that the existing Southern Ocean temperature and salinity biases cause a rapid transition to a high melt regime under the Filchner-Ronne ice shelf. So that's sort of highlighted in red here. And after some exploration, we performed a simulation, which I'm calling VGM, which has a stratification dependent coefficient in GM, and found that sufficiently mitigated some of the biases that we're seeing that were key to avoiding this tipping point behavior and resulted in a stable configuration. And so those are the orange lines on the right here. So if we look at the total pan-Antarctic ice shelf basal melt flux, we'll see that these remain within bounds of current observational estimates, which are these green and purple boxes here. The time slices are arbitrary since these are present day estimates compared against a pre-industrial forced simulation, but just to give an idea that we were able to achieve some stability there. And so I just want to point out, there's a lot of panels on this slide, but I just want to point out a few points here of how the VGM simulation was able to reduce some of the temperature and salinity biases that we see that are key to avoiding this tipping point behavior. So I'll start with focus on what's circled here is the Filchner-Ronne ice shelf. And we see in the CGM simulation, we're getting strong warming at the seafloor, which is in this red circle here. And eventually this warm water that's intruding from depths below onto the continental shelf, once that intrusion gets strong enough, then the warm water gets under the ice shelf and causes a rapid melt regime or a rapid transition to a high melt regime that's then sort of unrecoverable to come back to anything close to present day observations. And that bias is mitigated in the VGM simulation. Similarly, maybe I'll or emphasize on or focus on the salinity biases, but really it's the surface fresh bias that's quite strong in the CGM simulation, that's significantly lessened in the VGM simulation. And so that's all I want to say about the V1 campaign, and I want to focus the rest of the time on how things are looking for V2. So our V2 science question is how will the atmosphere, ocean, and sea ice systems mediate sources of sea level rise from the Antarctic ice sheet over the next 30 years? And for our V2 simulation campaign, in addition to the standard low resolution configuration, we're also making use of the variable resolution capability of E3SM and have developed a Southern Ocean regional and refined mesh for the ocean's sea ice components. And so this goes down to about 12 kilometers all around the Southern Ocean, extending up to about 40 kilometers in the tropical Atlantic and 60 kilometers in the tropical Pacific. And so this, in fully coupled configurations, is still paired with the standard low resolution atmosphere. So our plan is to do about 200-year spin-ups or so for under 1850 conditions for the low resolution configuration, and 1950 conditions for what I'll be calling the SORM configuration. And then from there, provided that we have simulations that can reach some sort of equilibrium, which seems promising, then we'll be able to start doing historical simulations, SSP scenarios, as well as a 4 times CO2 scenario. And so the ability to do these, finally being able to move past pre-industrial and into actual projections are sort of key to being able to answer our V2 science question. So some preliminary results. I'm going to first focus on a pair of simulations that we've done that were run using the V2 water cycle pre-industrial control tunings. And so these are both under 1850 conditions. We've only just recently started running SORM under 1950. So for now, we'll just stick with 1850. For the low resolution, we've run 300 years. And for SORM, we've run 100 years. So the time scales are different on the time series, but I want to show the full results that we have. So for low resolution, we're seeing this sort of steady increase, but I think you can argue in the last 50 years or so, at least the Pan-Antarctic melt fluxes are reaching some sort of equilibrium, albeit far too high. And this is largely driven by the East Antarctic ice shelves that are just experiencing far too much warming. But at least this is a sort of a gradual transition that seems to be approaching some equilibrium, rather than these sort of problematic cases where we were seeing a tipping point behavior that was drastically causing the model to transition to a completely different state. The results from the SORM configuration, on the other hand, are showing too little melting, but there's does not appear to be any sort of strong linear trend, so it's at least reaching equilibrium a bit quicker. So as I mentioned, the key problematic behavior of the Filchner-Ronne ice shelf transitioning to a high melt regime seems to not be happening with all of the changes that have happened to the ocean and other components from V1 to V2, which is very encouraging for us. Although there are still, and particularly low resolution as mentioned, I just wanted to point out one particular ice shelf, the Amory ice shelf, that's a really large driver of this sort of systematic increase in melting that we're seeing. So now I want to sort of point out some of the particular problems that we're seeing, and I'm really going to be focusing now on the SORM configuration, as that seems to be sort of the most promising avenue for us to be able to pursue some of these future scenario simulations. So one thing that I wanted to point out is as sort of a standard or known bias in E3SM, not just in the cryosphere configurations, but also in water cycle, is that there's a strong fresh bias. And this is particularly strong in the Southern Ocean, which can be a bit problematic for us if we're trying to represent the Southern Ocean climate. And this fresh bias is significantly reduced in the SORM configuration compared to the low resolution. However, this may be a case of sort of compensating errors, which will be clear in the next couple of slides. So this is the summer sea surface salinity biases. And next I want to look at the seafloor temperature biases. So these are something in the cryosphere that we look at pretty regularly, because these are sort of strong indications of how the ice shelf melting is going to respond. So I'm highlighting, this is the Amundsen Sea, Bellingshausen Sea sector in these red circle lines. And so we go from a slightly warm bias in the low resolution simulation to a very cold bias in the SORM simulation, which was something that I think we were initially not quite expecting. And so this is causing sort of this whole sector of the ice sheet to experience very low melt rates, which is really driving the underestimate of the ice shelf basal melting in the SORM configuration. And I also just wanted to highlight, this is the Amory ice shelf that I had shown the time series from before, and in the low resolution simulation, this is experiencing very warm continental shelf ocean conditions, which is driving the high Amory melting. But in SORM configuration, we're looking pretty good. So moving from the, so sort of focusing on the Amundsen Sea sector, so I'm showing a transect here across the Amundsen Sea in the low resolution and SORM configurations. And what we're noticing that in the SORM configuration is that there's this very strong Antarctic slope front that's blocking any intrusion of warm water into the ice shelf cavity, which is not indicative of what is actually happening. So this middle panel is it's a state estimate, but about the best that we have to compare to. But we do know that these shelves here are generally warm shelves and are under present day observations experiencing rather high melting. So this strong slope front is certainly a concern in the SORM configuration. This is not present in the low resolution, although it's allowing a little bit too much warm water on there, but it's at least structure-wise more indicative of what is currently observed. And a second sort of key problem that I want to point out in the SORM configuration is the summer SST biases are getting very strong, in particular in this circled section of the ocean. And this is then leading to, or I guess the driver of this seems to be that there are very strong events of vertical mixing in the ocean that's bringing up warm, slightly saltier water from depth up to the surface. So these are plots of the mixed layer depth, both for the entire Southern Ocean on the top for low resolution and SORM, and then just sort of close to this sector where we're seeing this very high warming, and the eastern Sea. And so the red dashed lines that I'm putting for reference on the right side here are really the maximum of what we're seeing in the low resolution simulation. So everything that's above the red lines on the storm configuration under the storm simulation is just giving an indication of how much stronger the vertical mixing is occurring in this simulation. So this is bringing all of this warm water at depth up to the surface, causing this very strong surface warm bias that then leads to essentially inability for sea ice to form in this area at all. So I'm showing, this is now only SORM showing the sea ice concentration and thickness. And so we're essentially losing all of the sea ice in this sector. And then this feeds up to the atmosphere, where we're seeing strong differences in the radiation budget. So what I'm showing here is the difference between the SORM configuration and the low resolution configuration for the last 50 years. So this lack of sea ice, this lack of insulating layer in the ocean is having a strong effect on the radiative balance in the atmosphere, which then leads to differences or to changes in the temperature and precipitation fields. So this sort of cascading effect from there's far too much vertical mixing, leading to far too much heat at the surface, leading to a lack of sea ice, feeding back to the atmosphere is clearly a problem for being able to represent the Southern Ocean climate properly. So we've learned from V1 that the mesoscale eddy parameterization can have a strong effect on the state of the Southern Ocean. And the key difference between the low resolution and SORM configuration, apart from resolution alone, is that the GM parameterization is scale aware and is turned off at when resolution gets high enough. And so around the Southern Ocean, where the resolution is 12 kilometers, by default, the GM is turned off in the SORM configuration. However, at this high latitudes that high, 12 kilometers is too coarse to fully resolve these mesoscale eddies. So we began looking at sort of tuning simulations, looking at different parameters or basically turning the knob on different GM parameterizations. So I'm going to now show some results of 50-year tuning runs that we did. So we have the default GM off, which I've been showing so far. We ran 50 years with GM on, just the constant GM. So then this would be the same setup as the low resolution configuration. And then a sort of middle ground where we're using not a constant GM, but what's known as the Visbeck GM parameterization with a minimum threshold set on the kappa coefficient so that it can't be completely turned off in the Southern Ocean. And I'll sort of lead with what to expect for the next couple of slides, that the GM off and GM on will be sort of end case members where well, we've already seen the GM off results, but the SORM configuration with GM on is going to look very similar to the low resolution simulation. And this, what I'm going to call GM taper, is sort of providing a middle ground between the two, which is sort of exactly what we're after. So I'll start with this strong summer SST bias is reduced with GM completely on, is still reduced with a GM taper, but sort of providing a bit of a middle ground between the two. So this is at least encouraging in that respect. And in terms of the seafloor temperature that we were seeing over in the Amundsen's, Bellingshausen Sea sectors, we were seeing this strong cold bias in our default configuration. With GM on, this is looking very much like the warm bias that we were seeing in the low resolution configuration, but we're sort of hitting a happy or a nice middle ground with this GM taper simulation. So here I just want to show the temperature and salinity diagram for this sector. So the sector that we're averaging over is highlighted in blue here. So where the middle and right panels are a reanalysis product and observations. So that's what we're comparing against. And we can see in the default configuration, the TS diagram looks very different. The temperatures are far too cold and slightly too dense. And the GM on looks a bit better, but sort of is compensating in the other direction, whereas this GM taper is really providing a nice middle ground and matching, provides a much closer match to the reanalysis and observation products. And finally, just to show some the impacts on the total Antarctic ice shelf melt time series. As we saw before, the default configuration is far too low. With GM on, it is higher, but there's you can start to see this the beginning of this increase that we were seeing in the low resolution behavior. And with the GM taper, things are looking a bit more stable and closer to observations. So I'll just point out just a hiccup in the in this run that there was an incorrect parameter set around year 30 that was then fixed. So that's why there's this sort of jump. But if we look at the last 20 years here, they're much more in line with observations. And so just to sum up, our V1 simulation campaign had this tipping point behavior that was leading to simulations not reaching an equilibrium that we could reasonably progress to scenario simulations from, and we were able to successfully mitigate that with by tweaking the GM parameterization. And in terms of looking forward towards V2, the preliminary results are much more encouraging to us than what we were seeing with V1, although there are still problematic biases that exist, but we seem to be reaching a nice middle ground by tuning this parameterizations so that we should be able to achieve stable simulations and finally begin transient in future scenarios. And that's it. Thank you.